Okay, we are going to look at the Unit 7 review, and this is part 1. So this is mostly just dealing with similar triangles. There'll be a couple other pieces in there too, but for the most part, this is similar triangles. So before we even begin, let's just kind of quickly review similar triangles. How do we know two triangles are similar? So we have 3 theorems, and I've listed them here. So I'm going to kind of highlight a couple important pieces here. So first theorem that we have is our angle triangle similarity theorem. And that basically just says, right, if 2 angles of one triangle are congruent to 2 angles of another, then the 2 triangles are similar. Okay? So we're looking in that case for 2 congruent angles of one and two congruent angles of another. So, okay? Next, we have the side triangle similarity theorem. And this basically says if the 3 sides of one triangle are proportional to their corresponding sides of another, then the 2 triangles are similar. So just quick reminder on what that means. So I'm just going to kind of draw this down here and then I'll erase it. Let's say I have these 2 triangles, okay? And this triangle, actually, let's make it look a little better here. So small, a little larger, okay? So let's say, and this is just obviously not drawn to scale. Let's say the length of this one was 1, the length of this one was 2, and the length of this one was 3. Okay, and then we had another triangle, and maybe it looked like, so the length of this one was 2, the length of this one was 4, the length of this one was 6. If you notice, if I took the small sides and I looked at their proportion, right? So the small side of the first triangle is 1, the small side's length of the second triangle is 2. So 1 is to 2. That's a ratio, right? If that ratio stays the same for all 3 triangles, so now let's go and look at the middle size one, right? So the middle size ones are length 2 and 4. If these fractions or if these ratios stay the same throughout, then these 2 triangles are similar. So let's look at the last one. 3 is to 6. And if we reduce this, right, it is 1/2 equals 1/2 equals 1/2. So all 3 of those side proportion, the proportion of all the corresponding sides are the same. Therefore, the triangles are similar. So that's just what they mean by that. Quick review on that. I'm going to erase that. Okay, and then the last one is the side angle side similarity theorem. And it's kind of a mix. So it basically says if 2 sides of one triangle are proportional to the corresponding sides of another, so just kind of like we did before, except we're only dealing with 2 sides, but they also have an included angle that's congruent, then the triangles are similar. Again, reminder, similar does not mean congruent, right? All that means is that the angles are the congruent, but the sides are proportionally the same. So that was just a quick review on our theorems. Let's go through and see if we can determine if these triangles are similar. So let's look at the first one. We want to determine if these 2 triangles are similar. So let's see if some things that we know. Again, we're trying to kind of fit into one of our theorems. So let's look at, notice we have triangle ACB and triangle ECD. Notice I know these 2 angles right here. Okay, I know that angle BCA, and so I'll just kind of write down what I have here. So angle BCA is congruent to angle, what is that? ECD. And the reason we know that is their vertical angles. So the vertical angle theorem. Okay, again, we're not doing a proof. I'm just kind of justifying it. And this is my justification. So I have those 2 angles are congruent because they're vertical angles. What else do we know? Well, I think you'd agree because the lines are parallel, right? Angle A is congruent to angle D. How do we know that? They're alternate interior angles. So angle D is congruent to angle A. I know I kind of said that backwards, but it's the same thing. and that's the alternate interior angle theorem. So I think you'd agree we're ready to go. Those two triangles are similar. How do we know they are similar? Because of the angle side theorem. So I'm going to kind of take this one with number 2, because number 2 says write a similarity statement for the triangles that are similar above. So I know these two triangles are similar, so I'm going to write a similarity statement. The similarity statement just says that we're taking the congruent angles and we're matching them up. Okay, so we're showing how everything matches up here. So I'm going to say, since I know that angle A is congruent to angle D, I also know that angle BCA is congruent to DCE. I'm going to say angle C and C. And then what else? Our last ones are B. And what am I missing here? E. So these two triangles, right? These two triangles are similar. How did I know? The angle triangle similarity theorem. I'm going to abbreviate that so I have some room. Triangle similarity theorem. Okay? Let's move right along. Let's just make sure I didn't make any mistakes there. I think I'm good. So angle A is congruent to angle D. That is correct. Yeah, everything looks good. Okay, so let's move right along. Let's move this over just a tad. Get it out of the way there. Okay, so let's see what we can do here. So first off, there are no angles. So I think you'd agree the angle theorem is not going to apply, and neither is side angle side, because we have no angles whatsoever. All we are given is sides. So what I want to see is, are the sides proportional? So I'm going to actually erase this purple stuff here just so that maybe I'll leave it. I'll leave it. Let's see if I can fit all this in. Maybe I might need to lower some stuff here. So let's go and see. What I want to see is the ratio of the sides the same. So in other words, let's start with the small sides. Okay? So I want to know, is AC, is the ratio of AC over ED, right? So let's just for naming's sake, I'm going to call this triangle 1 and this one triangle 2. So is a small side of triangle 1, I'm looking at the ratio of the small side of triangle 1 to small side of triangle 2. So I said AC is to ED. Is that the same as, let's go to the middle size one. So AB is to ED. And then finally, the large sides of those triangles, BC is to EF. So the question is this true? If this is true, then these two triangles are similar. If it is false, then they're not. If even one of them, if even one of those fractions isn't the same, then we're done. Okay, and it's not true. By the way, I want to just kind of keep note here. And this is important, I want you to notice that I always kept, in the numerator of my fraction, I always kept the lengths of the first triangle. And in the denominator, I always kept the lengths of the second triangle. You have to be consistent, okay? So you have to always go from one triangle to the other, but you always have to, whatever, the numerator always has to be the first triangle, and the denominator always has to be the second. I shouldn't say it. That doesn't have to be true. What has to be true is that you stick with the same triangle always on top and the same triangle always on bottom, okay? So that's really important. You can't mix. I can't say, for example, AC is to ED, but then switch around and say EF is to BC, because then I've switched my stuff around here. Okay, let's continue. Let's continue here. So let's put in some numbers. So AC is 6. ED is, what is ED? 5. Okay. AB is 14.4. And ED I said ED again. I noticed that. That's not correct, is it? It was DF. Let's correct that. That was a mistake on my part that I did not notice. So DF is 12. So let's just make sure we're good since I messed up on that one. AB is the DF. Looks good. And then let's continue. Last one is BC, which is 15.6, is to EF, which is 13. So I want to see if these three things are the same. So I'm going to grab my calculator. There's no reason to get crazy here. I'm just going to grab my calculator and say, okay, what is 6 divided by 5? 6 divided by 5 is 1.2. Does that equal 14.4 divided by 12? And the answer is, well, that's 1.2. Now remember, I still have to look at the last one because there's supposed to be three sides. So is 15.6 divided by 13 also equal to 1.2? And the answer is yes. Since the ratio of all three since these ratios are the same, right? Since these sides are proportional, then by side angle side, these two triangles are similar. So let's go and make our similarity statement. I am going to, let's lower this just a little bit so I have some room, especially because we're not even using this one. Okay, so what do we got here? Let's make our similarity statement. So let's see. I'm just going to quickly mark so I don't get lost here. So we said AB is congruent, or sorry, not congruent. It is similar to DF. So I'm going to say triangle ABC is similar to triangle, and let's make sure we have it. So A to B, which is D to F, then it goes, yep, so it goes to DFE, right? AB was a middle size side, DF was a middle size side, BC was a large side, FE is a large side. That works, okay? So those two are similar. How do we know? That is side, 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 triangle similarity theorem. Okay, so again, that takes care of questions actually 1 and 2, because number 2 was asking for the similarity statement. And again, this is the similarity statement. These two things right here are the similarity statements. And then number 1 was asking us for our justification. Okay, and we have that. So actually number 1 and 2 are both done. Okay, let's move right along. So use similar triangles to find the missing lengths. Now, this one's kind of interesting because it's telling you that they are similar triangles, and you could just move on saying, okay, I know they are similar triangles, so and they're not asking you to prove it, okay? But normally, a better question might have been, if they are similar triangles, then go find the missing length, okay? But, so let's just, even though they're not asking for it, let's just confirm for ourselves that these triangles are similar. Okay, so in the first triangle, right, if I were gonna, I'm gonna put in some labels here, and then maybe I'll erase them, I don't know. I'm gonna call this triangle right here A, B, C, and then the big triangle, right, would be DEC. So let's just make sure that triangle ABC is similar to DEC. Again, we don't have to, but let's just confirm it for ourselves. So both triangles, notice, both triangles contain the angle C, right? So if we were looking at our triangles, if we were going to write a similarity statement, right? Both triangles have angle C. Perfect. Then notice, because the AB and DE are parallel, by the corresponding angle theorem, I'm going to mark it in green, this angle right here is congruent to this. Now you might say, okay, but this one's also congruent to this. And that would be true. So all three angles are congruent to each other. So we know that the two triangles are similar to each other. So if we wanted to write a similarity statement, which we don't have to, but we could say triangle CDE is similar to triangle, what do we got here? CAB, CAB. Okay. Again, it's not, you're not being asked to show that they're similar, but we can just play with it just to show. I mean, just to see that. So let's go through and use our triangle similarity. Let's see, since we're using similar triangles, I'm going to erase this, by the way, just to get it out of the way. So since we know the triangles are similar, let's go find our lengths. So what do we know? Well, since the triangles are similar, their sides must be proportional. So in other words, the length of AC, right? The length of AC to the length of CD. Make sure we notice, right? I'm looking at this length is to this entire length, okay? So those two, since that length, that length, because the triangles are similar, the ratio of those two has to be equal to, doing this in finger paints, has to be the same as, what did I do? I did AC, so I'm gonna say AB is to DE. Notice the top side is the small side of it goes from small triangle to large triangle, and the second fraction again goes small triangle to large triangle. I'm trying to be consistent here. So let's plug in some numbers. AC is 6. CD is 6 plus 3 or 9. And then AB is 8, and DE is X. So let's go find the missing length. So we're going to solve this. Now I'm going to actually simplify if you don't mind. So 3 goes in both top and bottom, so I get 2/3 equals 8 over X. Then I'm going to do the cross product. So 2 times X is 2X. 3 times 8 is 24. Divide both sides by 2, and I get X equals 12. Let's move on. So looking at the next one, notice we can they're asking us again to find the missing length. If we wanted to show the triangles are similar, I think you'd agree. In this case, we have two angles are congruent to two angles of another. Absolutely, they are similar. So what are we going to say here? So I'm going to say, let's go triangle 1. Triangle 2. And I want to be kind of clear this. I've been kind of emphasizing it, but I'm going to when I go to write my ratios here, it's always going to be triangle 1 on top of the fraction, triangle 2 on bottom. Okay, I'm going to be consistent. So I'm going to say the small side of triangle 1, which is a length of X, is to the small side of the triangle 2, which is 2X minus 3. And that has to equal, well, the remaining side, right? So that hypotenuse, 7, is to 9. So that has to be true. Okay, so then again, I'm going to do cross product to go and find my missing number. So 9 times X is 9X, and 7 times 2X minus 3. So this becomes 9X equals 14X minus 21. Let's move some stuff over here. So I'm going to, let's just make sure I didn't mess up. 14x minus, nope, looks good. So let's subtract 14x from both sides. That gives me negative 5x equals negative 21. Divide by x by negative 5, and I get 21 fifths equals x. Okay? So let's move right along. Trying to think if there's anything else. Nope. Okay. A tree casts 100-foot shadow. So I'm gonna, because this is a word problem, I want to kind of get a picture of what's going on here. So I have this tree, and I'm just gonna this is my tree here. I don't know right? This is my tree. And it casts 100-foot shadow. So I'm going to draw that shadow in purple. and we know that it is 100 feet. Okay, now because it's casting a shadow, right, I'm going to do this in, let's say, orange. So imagine this is kind of the light, right, the sun's rays, and that's it forms a triangle. Okay, then what do we have? We have a 5-foot girl, so I'm going to draw a 5-foot girl. So boom. Whoops, that would be really long. Well, okay, this person's going to have some really long legs. Okay, so here's my 5-foot girl. She casts an 8-foot shadow, so our shadow might look like this, and it is 8 feet. Again, these triangles are not drawn to proportion or not drawn to scale. Okay? So, and we were told she is 5 feet. The question is, how tall is the tree? Well, again, we're going to set up our two triangles, right? These triangles are similar. How do we know they're similar? Well, we know they are similar because since the angle from the sun has to be the same, because it's going at the same time of day, this angle right here has to be congruent to this angle right here. And also, the tree is going to be perpendicular to the ground. And I know it doesn't look like it, but she's going to be perpendicular to the ground. Okay. Also, if you wanted to, you could note that this angle right here is going to be the same as this one right here. Okay. So these two triangles are similar triangles. And again, we didn't need to prove it, but we just kind of looked at it real quick and showed that it was. So what do we have? So in this case, what I'm going to say is, I don't know the height of the tree. So if you don't mind, I'm going to say the height of the tree is X. So if this is triangle 1 and this is triangle 2, I'm going to be consistent. So it's going to be triangle 1 on top of the denominator, triangle 2 on the bottom. So I'm going to say X is to 100. So the height of the tree is to the length of the shadow. So now I have to go is to the height of the girl, which is 5, to the length of her shadow, which is 8. So let's solve this. So 8 times x is 8x. 5 times 100 is 500. Dividing both sides by 8, I get 500 divided by 8. I'm going to put that into a decimal. So 500 divided by 8 is 62.5 feet. Okay, so the tree is 62.5 feet. Let's move along. And this got kind of moved when I was doing stuff, so I'm going to lower this here. Okay, find all the missing side segment lengths. Give an exact answer. So you've seen this before. This was one of the lessons that you've done. But let's just kind of remind you what's going on here. There are 3 triangles that we can see, and I'm going to label each of the triangles in green, I think. So triangle 1 is going to be this little triangle. There's a little triangle right here. Triangle 2 is going to be kind of that middle-sized triangle, and then triangle 3 is going to be the big one, right? The entire triangle itself. So I'm going to label that on the outside. Again, green or not, these are just labeling purposes. So these 3 triangles are similar to each other, and we could prove it pretty easily. And you've seen it in the lesson that they are similar, but we know they are similar. Let's go from there. So we know they're similar. Let's just start from there. So because the triangles are similar, what I can do is I can take sides that are corresponding and their ratios have to be the same. So let's see what we got. And I have those numbers there. I know they're a little confusing, but let's remember that the green numbers are not actual numbers that we need to look at. So what I'm going to do is I'm going to start with, let's see what we know. Let's go find one of our sides. We have a couple things we could do here. I think you'd agree. One thing I could do is I could go and find the value of x using Pythagoras theorem, but I'm going to not do that. I'm going to go and find the value of y. Let's start there. And this is just kind of my thinking out loud. So what I'm going to say is I'm going to say I'm going to look at two triangles here. So triangle, I'm going to highlight these in orange, and then I'm going to start erasing. So this is triangle one. I'm going to look at this little triangle right here. Let's make that a little thicker. Boom. Okay. So I'm gonna look at these two triangles right here. So this triangle right here, again, they're all similar, right? That orange triangle is similar to the triangle number 3. So triangle 1 and then triangle 3. I'm looking at triangle 1 and triangle 3. So what can I say? Okay, well, I can say the short side of triangle 1, right? So let's look at that. This is the short side of triangle 1. Well, that, side length, which is 6, has to be, the ratio of that has to be equal to the, well, not the ratio. That, let's make a fraction with those short sides. So 6 is to the short side of triangle 3, which I think you'd agree is this. So those ratios, that ratio has to be the same as, let's go to their hypotenuses. So the hypotenuse of triangle 1, which I think you'd agree is 10, as the hypotenuse of triangle 3, which is 6 plus y. So 6 plus y. Okay, this is solvable. So let's see what we can do. So multiplying, I get 10 times 10 is 100, and 6 times 6 plus y is 36 plus 6y. Correct? Yes, 36 plus 6y. So subtracting that, I get 64 is to 6 equals 6y, and dividing 64 by 6, I'm going to keep this as a fraction, and I know that the numbers are kind of bad, but I'd like to keep this as a fraction here. So let me just make sure. So this is 64 divided by 6 equals y. Dividing top and bottom by 2, I get 32 divided by 3 equals y. And I'm just going to keep them as exact values here. Okay, so we found y. So we now know that y length is 32 over 3. Now I want to remind you, we can use that if we want to. I don't have to use it, but I can. Let's see what else we can do. Okay. How about we go something kind of similar. Let's see here. Let's kind of erase this orange stuff here. I'm going to use triangle. I'm going to look at triangle 1 and triangle 2 to find the value of x. Okay, so let's see. Can I do that? I think I can. Let's see. Let's make sure I have enough information. I do. I'd like to avoid using 32 over 3. Let's see if I can avoid using 32 over 3. So let's see. I'm having trouble seeing how I wouldn't use 32 over 3. I mean, again, I want to emphasize, I could use 32 over 3 if I want to use similar triangles, but I really would like not to because the math is a little bit harder. So let's do this instead. Again, I'm going to do it two ways. I'm going to use 32 over 3 one way, and then I'm going to do the easier way after that. So let's just go and use 32 over 3 now, and then, like I said, I'll use the easier way. So let's see what we got. I'm going to say, for triangle 1, I'm going to say the short side of triangle 1, which is length 6, let's do it in purple. So, which is length 6, is equal to, that ratio from short to short, so 6 is to x, that has to equal the long sides of the two triangles. So the long side of triangle 1 is length x, the long side of triangle 2 is 32 over 3. And I said, as I told you before, this is where it gets a little confusing because we have that second fraction is a complex fraction. It's not a big deal, but we can deal with it. So multiplying across, we get 32 thirds times 6 equals x times x, or x squared. Kind of nasty, right? Okay, let's see what we got here. So this becomes, if we wanted to, 32 over 3 times 6 over 1 equals x squared. Notice I can cancel out a little bit here. So I get 32 times 2 is 64 equals x squared. So x equals plus or minus 8. But of course, this is the length of a side of a triangle, so x equals 8. Now, I do want to emphasize, that was fine and it worked great, but we could have also found x using Pythagorean's theorem. So I could have said 6 squared plus x squared equals 10 squared, and I could have solved it that way. So 36 plus x squared equals 100, x squared equals 64, and we're back at this step, okay? So again, either works. There isn't really any reason to box yourself in. If you've got multiple methods and you see one that's easier, then use it, unless you're being told specifically to use something else. Okay, let's go find the last one, and I'm going to go put that number in. Why didn't that delete? So we know that x is, what did I say? Its length is 8, and that's going to be pretty useful, I think, because now I can go and use that side, and it's a nice number. So let's see what we got. We still need to find z. So how about we go from, I'm gonna go triangles 1 and 2 again. I'm gonna go triangles 1 and 2. So I'm gonna say 6. So 6 is the 10, right? Short side of triangle 1 is 6. Short side, oh no, I'm sorry. I'm doing, no. I'm not going to do that. I could, but I'm not going to. So let's see what I'm going to do instead. I'm going to say, what did I say? I want to do, what triangles I want to do again? Let's just check. There's lots of ways of doing this. So let's see what I'm going to do. I'm going to do, how about triangles 1 and 3? Yeah, I'm going to use triangles 1 and 3. Let's see. Short is too long as short is too long. Yes, that's what I'm going to do. So I'm going to use triangles 1 and 3. So triangles 1 and 3. So for triangle 1, the short side of triangle 1 is 6. Is 6, and the short side of triangle 3 is 10. So in other words, I can say 6 is to 10 as, let's see, now I'm going to go hypotenuse of each of those triangles. So the hypotenuse of triangle 1 is 10. The hypotenuse of triangle, that's not finding what I want to find. Let's remove that. Sorry, I don't know why I thought that. Let's do triangles 1 and 2. Sure, let's do triangles 1 and 2. Okay. So let's backtrack on that. So I'm going to say short side of triangle 1 is the short side of triangle 2. So this is to this. So 6 is to 8. Then I'm going to do, since I'm trying to find the hypotenuse of triangle 2, I have to use the hypotenuse of triangle 1. So the hypotenuse of triangle 1 is 10. The hypotenuse of triangle 2 is z. Let's make sure we got it. So short side is to short side, right? And then hypotenuse is to hypotenuse. Looks like it's going to work just fine. So simplifying this, we get 3/4 equals 10 over z. 3z equals 40. So z equals 40 thirds. Okay? And that is our different values for those two triangles. Let's keep on going. Let's do B. Okay, so I'm going to, as you can see, these things kind of fell apart a little bit. Let's see what I can do. I don't want to lose my stuff here.